Okay, so I got this function here, and I've got a point on this function, and I want you to identify what could you tell me about partial respect to x and the partial respect to y at that point right there. So looking at that, let me just do it. What could you say about the partial with respect to x and the partial with respect to y at that highlighted? Does the red show up right there at the point? Yep. What could you say about the partial with respect to x and the partial with respect to y at that point?
Yeah, I mean, I thought, but I don't know. It looks
Okay, that plane that I just added, does that help you? Does that help you determine the partial with respect to x or the partial with respect to y? Right, it's a constant x, right? It's a constant x. So what do you say about the partial with respect to y? Okay, do we say it's increasing or do we say it's positive? Those are two different things. Right, so the value of z is increasing, therefore the partial derivative with respect to y is positive. Okay, so yes, z is increasing, therefore partial with respect to y is positive. What about to see the partial with respect to x? I'm going to take a constant y. Does that help? Partial with respect to x is negative because z is decreasing. So at that point, we got a negative partial with respect to x and a positive partial with respect to y. That's a little bit of review. Any questions about that? So let's take a look at already did that, so here we go. Second derivatives. So the second derivative, you could write it as fxx, or the partial of the first derivative with respect to x with respect to x. What does that reveal? Let's see. Anybody? So Ronnie, go give a shot.
Where the value of the function is like a max or a min.
Okay, so yeah, that'll max and mins will have to do with looking at the second partial derivative, but just the partial derivative itself exists, at other places too. So what does it tell us? Yeah.
We give you the concavity.
Okay, but so we want to do better than, yes, that's true, but we want to do better than that. We want to understand it in terms of rate of change, but yeah, concavity is part of it. Yeah, Emily. Okay, right, so it's the rate of change of the rate of change. Becca, is that what you're going to say? Okay. And what does that mean? The rate of change of the rate of change. So the second partial derivative is itself a derivative. So it's a rate of change. What's our meaning for rate of change? Yeah, Emily. Okay. So this, a lot of you are saying this, how the rate of change of z with respect to x is changing with respect to x. So it's like how the first partial with respect to x is changing with respect to x. Okay? So now we want to describe that with a sentence. How can we describe that? Practicing what we've learned now. Thinking of the second partial derivative as just a derivative of some quantity, right? or the rate of change of some quantity. We know what a rate of change means. What does it mean? We practice anyway, so did we return it? Did we retain it over the weekend? What is the rate of change? Okay. Nick thinks he has it. Samuel.
Given a small change in the partial derivative of x, z changes by fxx as much.
Okay, what are we gonna start with? What kind of change are we gonna start with? Change in. And we're not going to do a change in the partial derivative, right? We're going to do change in x, right? It's always a change in your independent variable, which is still x. We're going to let x change a little bit, and then?
I think f sub x changes by f sub double x times the change in x.
Good, right? So the amount that the partial derivative will change will be this rate times as much as how much you change in x. So given any small change in x, change in our rate of change with respect to x is going to be fxx times as much as dx, and it's worth fanfare. So do you see how this parallels what we were talking about before? But now rather than reflecting the change in z, it's going to reflect the change in the rate of change. Right? So it's the change in the rate of change is going to be this second partial derivative times the change in x that you pick. All right? So if the second partial is greater than 0, what can you conclude about the first partial derivative? What can you conclude about the first partial derivative if the second partial is greater than 0? The first partial derivative then is? Increasing, right? It means, so if this is positive, then this is positive, and that means we have an increasing rate of change. So what does it mean for the rate of change to increase? It means that fx is getting less negative. That's one possibility. The rate could be getting less negative. Watch it again. This is the rate of change of z with respect to x getting less negative, or it could be getting more positive. So the partial with respect to x is increasing. That means the rate of change is getting less positive, less negative, or more positive. And so then we say that the graph of z turns up. It's turning up. Whether it's going down or up, it's always turning up. Turning in the upward direction. And that's why it's concave up. It goes back to the fact that the rate of change is increasing, which makes the graph turn upward. And then you get a concave up shape. But concave up is like the most superficial thing. It's like the last conclusion. The profound meaning is that the rate of change is increasing. So that means it's getting less negative or more positive. That's the important thing. Okay? So now what about if the partial derivative with respect to the second partial with respect to x is less than 0? Then what can you conclude from this equation? These changes in the rate of change are? So if this is negative, then what about this? Negative also, right? So that changes in the rate are negative, which means that rate of change is decreasing. And so how can the rate of change decrease? One of two ways. Less positive, right? And what would it look like for the rate of change to get less positive? Like that, right? Higher, less and less and less positive rate, or you can get more negative. That's how the rate can decrease. And so when the rate is decreasing, the graph is always turning down, turning down. And that's where concave down comes from. If graph's turning down, then you get this concave down shape. Again, that's kind of the least profound or meaningful thing to say concave down. Much better is the rate is decreasing. The rate is decreasing, it's getting less positive or more negative. Okay, so let's practice that on the graphs. So this first one. So now I'm going to give you several different points, one at a time. So for this first one, we know that f of x, what do we say? It was negative, f of y, positive. But what about fxx and fyy? So is the rate of change in the x direction increasing or decreasing? Is the rate of change in the y direction increasing or decreasing? So I'll move it around. I'll throw some planes up there. You can talk about that. What do you think? Talk amongst yourselves.
X is getting less negative as we go on.
It's like accelerating down.
Oh yeah, I'm thinking like kind of like future behaviors. Yeah, it's getting more negative.
The y1 would be negative.
Yes.
Yeah, the y1's
Yeah, because I think what I want to do is this is more
Okay, partial with respect to x. So, second derivative, second partial derivative with respect to x. Positive or negative? Oh, that would be this one, right? The gold? Okay. Negative or positive? Is the rate decreasing or increasing? So z is decreasing. That's why this is 0. But what about the rate? Is it decreasing or increasing? Getting more negative, right? Isn't it getting more negative this way? So lower negative, higher and higher negative through there. Therefore, less than 0. And therefore the concave down shape, right? The concave down shape. What about partial derivative second with respect to y? Now, z is increasing, but what about the rate? Is it less positive, right? Less positive. Therefore, both are less than 0. Does that make sense? Okay. Any questions on that? Both are less than 0. All right. Let's skip to number... Okay. Try this.
Y is still getting more negative.
Yeah. Just wanted to do it without it first. Okay. Does this help with the partial respect to x or partial respect to y right here? X. And what do you guys think? Second partial respect to x. So, oh, but by the way, what about the first partials? What about with respect to x? Negative or positive? Definitely negative, right? Z is decreasing. In the x direction, Z is decreasing. Now the question is, the pen is impossible to control that. The question is, Is the rate getting more negative or less negative? Is it getting more negative or less negative? Yeah, it's pretty close to not changing at all, the rate. Do you see that? It's somewhere around here. So over here, it's getting more negative. And then here, it's getting less negative. Somewhere in here, pretty close to this point, it's the rate is not really changing. But do you think it's getting less negative? Do they need to move it back some here to get the actual 0? Okay, yeah, so I'd buy that. So I'd buy that it's positive, but pretty close to 0. Would you agree? Maybe if I moved it back a little bit more, it would be, you'd guess 0? That it's not, yeah, there's some that's called the inflection point, right? That's the point where it changes from, in this case, getting more negative, and then it changes to starting to get less negative. Okay, what about with respect to y? First of all, the first partial with respect to y, first partial, less than 0 or greater than 0? There's the first partial, the first partial. So asking about z, is z increasing or decreasing? Increasing or decreasing? No, right? No. What's it doing? Isn't that the bottom? It looks like the bottom to me. Is it the bottom? Okay, and then now what about the second partial with respect to y? For the very bottom, is it 0? Second partial? No, because all through there, the rate would be getting what? It looks like it's getting what? Less negative and more positive all the way through there, right? So all the way through there, the rate's getting less negative, more positive. So even at the bottom, so all through there, the partial with respect to y would be positive. So the second partial derivative doesn't hit 0 at the bottom. Z doesn't change at the bottom, but the derivative, the rate of change is changing all through there. It's getting less negative and then getting more positive. So that's second partial is greater than 0. Do you agree with that? Yeah.
So the second partial is only going to be 0 when it's like seemingly straight.
Yes, right. The rate isn't changing. That's a linear function, right? If the rate of change is not changing, that's a linear function, and that's like an inflection point or just linear. So somewhere in here, there's a place where the rate isn't changing, and that's where your second derivative is 0. Yeah. Oh, is that just any other questions? All right, let's look at one more. Just talk these out. So, first partial with respect to x, positive or negative? Negative. Z is going down, right? Second partial with respect to x, positive or negative? No, it's not getting less positive. It's getting more negative. The rate is getting more negative. You see that? The rate's getting more negative down there. So both the partial with respect to x is negative because z is decreasing. The second partial with respect to x is negative because the rate of change is decreasing. Agree? Okay, why? Partial with respect to x. Partial with respect to y. First partial with respect to y. 0. High point, right? So z, for a moment there, z is not changing. Okay, what about the second partial with respect to y? Negative. The rate of change is decreasing all through there. Less positive to more negative. So first partial with respect to y is 0 because z doesn't change. Second partial with respect to y, negative because the rate of change is decreasing in that direction. Okay? Very top. Partial with respect to x. Let's put both on here. The blue, is that helpful? Okay? Very top. Partial with respect to x. 0. Second partial with respect to x. Negative. Partial with respect to y. 0. Second partial with respect to y? Negative. And so here, so this is, Ronnie, you're getting at, so what do we have here? What is this? Local maximum, right? Local maximum. And what's happening at a local maximum? Our first partials are 0. Second partials are negative, right? Okay, last one here. What about this point? What do we got going on there? So, what about the partial with respect to x at that moment right there? Going this way. 0, no change in z, right? What are we coming this way? 0, no change in y. Is it a local max or a local min? Local max or local min? Yes. Yes. Is it local max or local min? Yes. You see what's happening there? Do you see that in one direction? Coming this way? Now this is not the x or y direction. This is kind of, oblique. Do you see what it is there? Do you see you have a local min if you're traveling in that direction? But if you go this way, it's a local max. So we have the first partials are 0, but that doesn't, so when both first partial derivatives are 0, it does not guarantee that you have a local max or local min. Here you have kind of both, depending on what direction you're going across that thing. Right? So this is called a saddle point. Because it's like a saddle, right? You could imagine, your legs are on either side here, and the front of the horse is here, right? So the easiest way to just sketch one of these is kind of like this. So right there, saddle point. See that? One direction you have maximum, another direction you have minimum. And you can have more than just one direction of minimum and one direction of maximum. You can have like multiple directions. I made it. There's another one I gotta find. But you can have multiple directions where, because you can go around in a circle, right? Like there's an infinite number of directions that you can go around there, and then like in several directions it could be max, but in between those several directions could be minimum. So it's not just necessarily one direction of max and one direction of min. You can have many. I'll show you next time. I'll show you. Remind me to show you my illustration of that. Okay. So we're kind of like, now that we're talking about second derivatives, we're talking about these like critical points, like local maxes, local mins, these saddle points. And so let's kind of define the math behind all that stuff. So a critical point means that both the first derivatives are 0. Okay? Both the first derivatives are 0. And so we saw the three types are local max, which is a high point in all directions, local min, low point in all directions, and a saddle point, which has at least one direction that's a low point and one direction that's a high point. But it could have more. And I'll show you that. later. So there's this to figure out once you have a critical point, there's this thing called this discriminant, and this is a formula, gives a number that helps determine what you have, local max, min, or saddle. And it's this thing here. So it's the partial, second partial with respect to x times the second partial with respect to y minus, so now these are the two second partial derivatives that we did not talk about. So this is the partial of y with respect to the partial of x, and then vice versa. But you've seen from previous web work, and I left it on you to learn this small fact. There's some web work problems that said what? Those are equal. Remember that? From a web work problem? We haven't discussed that yet in class. But those two are equal. So you can just calculate one of them and square it, because those are equal. In terms of finding the discriminant. Does that make sense? That was Clairaut's theorem. Clairaut's theorem says that those are equal. And when we get into vector fields, that we'll talk more about that. Clairaut's theorem becomes a lot more significant than just these two partial derivatives are equal, okay? All right, so there's the discriminant. And so if d is greater than 0, when you do this value, you have either a local max or min, but we know how to figure out which one it is. How do we figure out what we have? We know we have a local max or min, and what tells us which it is? We're just looking at examples of that. What would you look at to know? Yeah, Samuel.
If the second partials are negative or positive.
Right, so if the second partials are negative, which one do you have? That means the rate is decreasing. You have a max, right? And if the second partials are both positive, that means the rate is increasing. So you have a min. All right, and then the discriminant is less than 0. It's a saddle point, and you're done. You don't have to qualify anything about a saddle point. And then if it equals 0, then there's no conclusion. So you've got a situation where you have a critical point, but the discriminant didn't tell you what it was, so you'd have to use another means, like a graph or something, or testing points or something like that to figure out. But you rarely see this happening, right? For our purposes, the examples, you're going to get that d is greater than or less than 0. So again, we already talked about this. Max, second derivative, negative because the rate is decreasing. Min, second derivative, positive because the rates are increasing. So that's how you distinguish when in the d greater than 0 case. Okay, so let's look at an example here. So here's a function. 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. And so let's just look at the graph first. So this is not a graph that you'd be responsible for figuring out based on that equation, right? This is a more complicated polynomial than our basic paraboloids and cylinders, etc. Okay, so let's just predict. What do you see here for local max, min, and saddle? How many of each? How many local maxes do you see? 1, right? Right there on the z-axis. Local mins? 1 over here in positive y territory. And then how many saddles? 2. Okay, so that's what we'd be expecting. Okay, what about this one? Oh, where is it? Question. All right, so how many here? So, how many local maxes? How much time do we have? We still have 4 minutes. How many saddle points? Okay, so this is like the we're actually going to do a problem using this function. This is my Lord of the Rings function. And a couple next week or two, we'll be doing a problem with this. But you had a question?
I was going to ask it, where are the saddle points on the
Oh yeah, and the other one, yeah. That's the more important question. So where are the saddles? Do you see it? So there's a set like let's give you like right there. See that? Because it's like a minimum there in that direction, then a maximum this way. Can you see it? It's like that crease, like where you could sit, right? Can you imagine sitting in there? Throwing your leg on either side and sitting in there? Like right there.
Oh, I see.
And then there's one over there, too.
Okay.
Okay, so what does it mean to figure out where those are? What do we need? We need time, but we don't have that. What do we need to find to locate these? We need what? Partial derivatives, right? So here we go, quick. Partial respect to x is 6xy minus 6x. Partial respect to y.
Squared plus 3y squared minus 6y.
And if we were thinking about critical points, we're interested in where those are 0. So what do we need? Here's the key. When you're doing the algebra and you're trying to figure this out, just keep in mind you're looking for ordered pairs, combinations of x and y together that make both of these 0. So we're looking for ordered pairs so that you have an ordered pair and makes both of those equations 0, then you got a critical point. So we're going to work on this. Is easier to work on first. This first one, 6x times y minus 1. So the only ways to make f of x 0 are what? If x equals 0, or if y equals 1. So when x equals 0 first, then we're going to put that in here and figure out what y needs to be to make this 0. Does that make sense?
Yeah.
Then we'll have them both 0. So when x equals 0, f of y equals 0 plus 3y squared minus 6y, which gives 2 possibilities, which are y could be 0, y could be 2, and then with x equals 0, those two ordered pairs, 0, 0, and 0, 2, will make both equations 0. Does that make sense? Okay, and then what about from here, from the first equation? Y could be 1. And if y equals 1, then we get 3x squared plus 3 minus 6 equals 0. So 3x squared equals 3. And x could be plus or minus 1. So that gives us 2 more ordered pairs, 1, 1, and negative 1, 1. So then, I'll just give you the roadmap here. We won't finish it, but you got your critical points are 0, 0, 0, 2, 1, 1, negative 1, 1, and we've got to get fxx, fyy, fxy, and d for each of those. So getting the fxx, fyy, fxy is helping you get d. So you can make a table for this. So that means you've got to find the second derivatives, find this one with respect to x, find this one with respect to y, find this one with respect to y, and then plug in your values, x and y, and get all these values of these partials, second partials. Use the formula to get d, and then based on what I told you about d, determine if it's saddle or, and there's, right, look, 4, just like we predicted. A local min, a local max, 2 saddles. That's 4 critical points. Okay?